we're in motion too. So that's it. Now, if you took this, and that same law of motion should say that I should be able to throw this, and this should keep on going. Well, if I tried to throwing it, you can see obviously it's not going to go very far. Why? Because it's going to hit the wall, or gravity is going to affect it, or air resistance is going to affect it. But if it wasn't for gravity and air resistance and the wall, this thing would keep on going in a straight line, is what he postularized. Now, if it would accelerate, if it go faster, because when a rocket starts like this, if this is a moon rocket, it would have to travel 25,000 miles an hour, wow, to leave the bounds of the Earth to reach the moon 240,000 miles away. If you just wanted to go into orbit only 100 miles up, you wouldn't have to go 25,000 miles an hour, 8 miles a second. You could do a simple 18,000 miles a second. I mean, 18,000 miles an hour. And to do that, how would you get this thing to go that fast? It starts out at 0 speed, and it's traveling eventually 5 miles a second at 18,000 miles up. I mean, 18,000 miles an hour around the Earth, 100 miles up. And what happens is you've got a force that's coming out of this, and that force, even if it remains the same, you're consuming rocket fuel. And so the mass, even though the apparent size of it is still the same, the mass is becoming smaller and smaller. So in order to even stay that same force, that same equilibrium, and Dr. Kahn likes equilibrium, all right, then the acceleration has to increase. So the rocket would go faster and faster until it eventually uses it. One of those old rocket pioneers, Tsiolkovsky in Russia, he said, well, you can make it even easier if you had your rocket as trains. You hit, like, this is a train here, this is a train here, this is a third train. So we call them stages. So you drop off a stage, you drop off some of the mass, you increase the acceleration, and you eventually get this thing going 18,000 miles an hour. Have you all been to the Air and Space Museum in Washington? And you've seen the space capsule, the Apollo people came. What is that thing? That's about 10 feet tall. Okay. Well, that's the only part of the rocket that came back. The Saturn V rocket was 366 feet tall. But by successively dropping off the trains or the stages, we got that part to go to the moon, and then used gravitational forces and rocket thrusters to bring it back. It took about 3.5 days to get there and back. How about that? 42 years ago. All right, so body at rest, we takes off, it starts to accelerate. That force is going to equal mass times acceleration, which is kind of a neat thing. I'm going to share you with one other thing. I'm going to tell you a story about speed bump, and I'm going to tell you about a slug of metal only about yay big. Speed bump is a friend of mine who was working on his Volkswagen, and he was underneath the thing, and he hooked up 2 wires, and he didn't realize the thing was in gear. And so it started up, and he had the pleasure or the displeasure of watching the thing roll over him and then roll down the street. It was going so slow that he wasn't injured. When he knew his car was going to run into something, so he jumped up, not thinking of his injury, and ran down the Volkswagen, put on the handbrake, and the Volkswagen stopped. And then he started to worry about what in the heck just happened to me. Well, so if you have something that is very large and very massive, but it's traveling very slow, it might only exert a little bit of force, is what I'm saying. But suppose you have something a little, just maybe a ½ an inch wide and about yay long. If you can take that little piece of metal like that and throw it really fast, hundreds of feet per second, you know what we call that? We call it a 50 caliber bullet. So even objects that are small, little finger size, that are traveling hundreds of feet per second can exert a massive amount of force. NASA has a series of satellites that they call the A-Train. It has nothing to do with Duke Ellington. What it has to deal with is 5 satellites that are traveling in the same orbit. They follow one after another so that they'll all come over about the same local area. Bing, 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 bing. One measures atmospheres, one does temperatures of water and so forth. So they each have different sensors. But we have space objects, space junk that comes down and could impact these spacecraft. And so what happens, all I can say is, Ethan, you got to get out of the way of these things, because what's going to happen is the object could hurt the spacecraft. So we have to adjust the orbit of all 5 spacecraft to get out of ways of little bits of space paint, things, flecks of objects, of junk from other spacecraft, so we don't hit these things. And there is lots of stuff out in space. All right, so that's the force equals mass times acceleration, law of acceleration. All right? Hope I didn't bore you all on this. What questions you got?
Got it.
Okay, that's great. Now let's do the rockets. All right, we're going to build Alpha 3s. Probably some of you have built model rockets before, but this is great. What we're doing, we'll launch your rockets first, and Dr. Kahn has asked that we have some other rockets to launch. So we'll launch this one. Hopefully it won't go 18,000 miles an hour, 100 miles up. And he was talking about an egg rocket. Do we have such a thing? Unfortunately, Dr. Kahn, I brought the egg rocket.
Giving the egg.
And even worse than that, buddy, I brought the egg. We're going to put an egg up here. It's in here. I've got it all wrapped up so it won't crack. And then we'll see if the yolk's on me, all right? And then, in addition to that, I've got this one I built. I'm most proud of this one, and I'll tell you why. Because it took me longer to build the box than it did the rocket. But this is, see, look at this. I even put Velcro on the thing. I built this just for you guys. Believe me. I built a boost glider. I built my own space shuttle. I know you're dying to see what this thing looks like. Here it is. And it's going to have a little booster. Oh, this is going to be so much fun. Like this, and it's going to go on there. And I'm going to boost it vertically like this. And then the game plan is that it'll punch out a streamer right there. This will deploy, come down nice and safe, not leaving a crater more than a foot in the ground. And then this guy right here should glide away, and if we're lucky, maybe it'll hit Pennsylvania, okay? So that's what we're going to do later today. So that's what we're going to do. You're going to build an Alpha 3 rocket. And Alpha 3 will look like this. Parts of the rocket you should know about are what do they call these things? Fins. What do fins do for a rocket? Why do I need fins?
Stability of flight.
Stability of flight, right. Fins on a rocket act like feathers do on an arrow. If you took an arrow and you took off the fins on it, or the feathers, and you tried to shoot it, it would probably tumble like a pencil or something, you know. And so in order to keep the rocket from not tumbling, you use fins. Aerodynamically, when a rocket flies, it's got a lot of forces going at it. It has the force of the rocket engine providing thrust in one direction, that's the action. The rocket moving in the other direction, that's the reaction. But it also has air blowing against the fins, which act sort of like vanes on a weather vane. It has gravity, and it has air resistance going as the rocket travels, so which they call drag. So these are the fins. What do you think this nose cone has an interesting name? You know what it's called? Well, that's the shape of it. That's pretty good. Now this is called a nose cone. Okay, so that's what it is. Nose cone. This body tube is called a
Body tube.
Right. I knew you'd catch on quick. And the straw is called a launch lug. Right, not a straw. There's a trick question. Everything has its own terminology. You're taking nursing, you're taking medicine, you're taking anything. Everything has a patois or jargon or name for it. This one has a parachute. Cool. Right. Your parachute will look like something like this too. Have a big piece of elastic to keep the rocket together so you don't have to chase it all over the place. Two separate places. This elastic is called the shock cord. The string that covers holds the parachute together is called shroud lines. There's a little screw eye here in the nose cone. It's called a screw eye. And I think that's about it. There's an engine hook on the back end. That's to keep the rocket engine in place, because the way the rocket engine works, it's made out of paper, believe it or not. I'm running out of hand. Well, I hope that stays at rest. All right, it's made out of paper. It has black powder in it. We launch it by putting a thin little wire in the back end where there's a little nozzle. And then we don't light it with a fuse. We use electricity from a battery. I've got 2-car batteries. Why? I don't know. That's what I brought. And anyway, you put that voltage through that wire, and that wire will glow red hot like a filament would be in a light bulb. And that's what starts the rocket engine. The nozzle is tapered. It's kind of bell-shaped. So the gas that results from the black powder being ignited is expelled out the back end. It's very small, just little parts of gas, but it's traveling literally thousands of feet per second. And that generates the force, the action for the rocket to move in the opposite equal reaction. The rocket engine is consumed kind of like a cigarette, providing the power going the rocket up. At the top end of the rocket engine, there is a smokeless trail to allow the rocket to coast to reach its highest altitude. I'm thinking your rockets are probably going to go about 75 to 100 miles an hour, and they're probably going to go about 150, maybe 300 feet in about a second and a half. Wow, okay. And so what happens when the fuel gets up to this top part, there's a big hole at the top, and the gas has a choice of either exiting this hole at the top, big hole right near where it is, or it can travel all the way back down to the end of the rocket engine and go out that teeny little hole. So where do you think it goes? It goes out the top, takes the path of least resistance. And what that does is it pushes out the nose cone and the parachute, kind of like a piston. And that's what deploys this, and then hopefully we'll get it back and not into a tree. Okay? But when that gas comes pushing out here, what happens? The rocket tries to move in the opposite and equal direction, right? So we have a little hook at the end to keep the rocket engine from being expelled, because if the rocket engine was expelled, maybe the nose cone would stay on, and then this would come down just as fast as it went up. 100 and some odd miles an hour, 75 to 100 miles an hour. All right, well, there's the little parts, okay? Cool, you all ready for this? I went to your cafeteria, and guess what I found? Boy, this is the place to live, I'll tell you.
Blue trays.
Blue trays. If you go to the cafeteria, you will not find blue trays. You know why? Because I have them all. That's the answer, okay? There you go. There you go. Oh, I'm sorry you guys get no blue trays. I only had a few trays, so I'm so sorry. You'll have to settle for red trays. All right, so there. Now open up those darn things and put them in the purpose of the tray is there's lots of little parts like the launch lug and the screw eye, and I really don't want you fumbling around on the floor, so put everything in the tray and has a lip on it, and we'll satisfy it. Now, let's see. Our first step. All right, Kevin, I'm going to look at yours. First set, it gives you a part layout. It tells you everything. It gives you some more parts than we talked about. There is a Blue Robin engine mount tube. You'll see it probably in there, okay? And there'll be some centering rings. They're usually green. And I think the first thing I want to do is to take the engine hook, and you'll see on the engine mount tube, that's the Robin Blue tube, there should be a slit at one end. And you put the engine hook onto that slit. And if you get it there, it's okay. All right, I want to borrow your thing. All right. Kevin did that. This is what it looks like when you're finished, okay? All right. Okay.